Take the derivative of something called a differentiable. So in today's section, which is 2.1 part C, we're going to look at the relationship between differentiability and continuity. Now, in order to find our differentiability work, we're going to again look at our equation for slope with a tangent line, but I'm going to change the definition. Notice that my 2 points are defined as x and f of x and c and f of c. So now my slope and my secant line is f of x minus f of c divided by x minus c. So my slope of my tangent line would be the limit as the denominator, the change in x goes to 0. But instead of writing the limit as delta x goes to 0, we're going to write x minus c equal to 0, which we'll rewrite that to be x equals c. So this time we're going to rewrite our slope of the tangent line as the limit as x goes to c of f of x minus f of c divided by x minus c. This is called the alternative form of the definition of derivative, as compared to the derivative definition, the limit definition that we learned in the last few classes. So it means the same thing as the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. But we use this x goes to c because it allows us to find the limit from the left and limit from the right on our graph. So that's the reason we're going to be using this alternative definition of derivative. Just like we had one-sided limits in our previous chapter, we can have one-sided derivative. So the limit as x goes to c from the left of f of x minus f of c divided by x minus c is called the derivative from the left. Likewise, the limit as x goes to c from the plus side of f of x minus f of c divided by x minus c is our derivative from the right. We're going to use the derivative from the left, the derivative from the right to explain our very first theorem of the day. We're going to use this function to determine if a function is differentiable over an interval. So f is differentiable on the closed interval from a to b if the following three conditions are met. The first condition: f of x is differentiable on the closed interval from a to b if it is differentiable in the interior of the interval, so on the open interval from a to b. The second requirement is if the derivative from the right of the endpoint a, so if the derivative from the right of a exists. Lastly, if the derivative from the left of the endpoint b exists, then we can say the function is differentiable on the closed interval from a to b. So again, to use this theorem, we have three requirements. It must be differentiable in the interior of the interval, all of the points inside from a to b, and it must be differentiable from the right of a must exist, and the derivative from the left of b must exist. So the derivatives from the endpoints must exist. From this theorem, we can make the following deduction. Differentiability on an interval implies smoothness. That means we have a smooth, continuous curve connecting the dots. No strong corners or cusps or jumps or breaks in our graph. And when a function is differentiable, sometimes it's easier to figure out when a function is not differentiable. So we're going to look at the exceptions. So these are the things we're going to look at to figure out a function is not differentiable. First thing we look at is points of discontinuity. So anywhere the function is not continuous, it automatically is not differentiable. So we have to go back to our last chapter when we learned about continuity and look at the cases where we could have discontinuous points on a graph. In this first picture, I have jump discontinuity at c. So this function, f of x, would not be differentiable at x equals c because of the jump discontinuity. On this second graph, we have a removable point of discontinuity at x equals c. So therefore, the function is not differentiable at x equals c because of the discontinuity. In my third graph here, I have an infinite discontinuity at x equals c due to that vertical asymptote at x equals c. So my function is not continuous at x equals c, therefore it is not differentiable at x equals c. So anywhere the points are discontinuous, the function is not differentiable. The second type of non-differentiable functions is any point where you have a cusp or a corner. So these are sharp points or sharp turns on your graph. They would represent a non-differentiable point. On our first graph for part 2, I have a cusp at x equals c, so my function is not differentiable at c. In my second graph, this absolute value graph, I have a corner at x equals c. Function is not differentiable at c. And last, I have another cusp at x equals c. So this third graph is not differentiable at c. Notice that at these cusp and corners, our function is continuous, but it is not differentiable at x equals c. Whereas at the points of discontinuity, our functions were neither continuous nor differentiable at that point c. The third thing that we're going to look for to determine if points where a function is not differentiable is for vertical tangent lines. Now, a graph is not differentiable at a vertical tangent line because remember, our differentiability equation is the slope of the tangent line. And when our tangent line is vertical, as in this picture here, my slope is undefined. So I can't have my derivative equal to undefined. It does not exist if the derivative equals undefined. Third condition we look for is when the tangent line is vertical, and then we have a non-differentiable point at that C. Notice that vertical tangent lines are continuous but not differentiable at x equals c. So let's try a few. Here in examples A through H, I have graphed a few functions. I want you to tell me whether the functions are continuous, differentiable, neither, or both at the given points. Pause and try it, and then come back and check your answers. At example A, we have a discontinuity at x equals c. So if it's not continuous, if it is not differentiable, so this would be a neither. B, we have at x equals 1, we have a removable point of discontinuity. So this is neither continuous nor differentiable. At x equals c, we have its continuous function. And we look at the function. We don't have any cusps, corners. It's an all nice, smooth curve. So we would say this is differentiable and continuous at x equals 0. Part D, we have a cusp at x equals 0. So the function is continuous, but it is not differentiable at x equals 0. So we would say continuous. At x equals 2, we have a infinite discontinuity. So the function is neither continuous nor differentiable. So neither. At f, at x equals 0, our function is continuous, but we have a corner at x equals 0, so it is not differentiable. So this would be continuous, but not differentiable, so we'd write continuous. For g, we have a continuous function, but it has a cusp at x equals 2, so it's not differentiable, so we say continuous. At h, we have a vertical tangent line at x equals 1, so again, this is continuous, but not differentiable, so we would write continuous.